This is Frame by Frame Season 2, Episode 4. Today we'll be talking about some training mechanics that happen inside a neural network. In the previous video, we talked about some activation functions and what happens when the nodes get sent their data, apply an activation function, and send that all the way to the end until it reaches the very final layer where it's going to have the special activation function, the softmax function, and it's going to apply a percentage or like a guess on each class that's inside the data set that we have. Now, bear in mind that during the next couple steps I'm going to be talking about, it's going to be mainly applicable for the models that we have. At this point in the neural net, we can compare the model's output data to the actual ground truth labels. To do this, we'll use what's called a loss function that's going to compare our ground truth data to what we've predicted with using our model. Now, the primary goal of this loss function is to have a quantifiable number or a way to estimate how far off we are from the ground truth labels. A helpful analogy to think about is like a dartboard. So if we were to throw a dart at a board and we want to get a bullseye, but we're a little bit further away, the loss function tells us how far away we are from the actual bullseye. So if we're further away, the loss function will be higher. The neural network model is going to do the same thing. It's going to use that number and try to adjust its aim for the next iteration and the next one, trying to get closer to that bullseye. Now, before we talk about loss functions, I do want to touch base on how we actually break up the data and send it through the model. We can't simply just send 60,000 images through a model. That would just crash the whole system.
Oh, how long do you think that would take?
There's a couple different ways that we can use to describe how the data is actually moving through the model. We have iterations, epochs, and batches. These are pretty similar in like how you would use in a gym when you're doing reps and sets of an exercise. So if we were to send 60,000 images through a model at one time, that would be very computationally expensive and wouldn't really help us at all, and it would take forever to train. And what we can do is we can group it up into smaller batches, they're called, and send those batches through the model at one at a time. Usually we can group up images, about 32 to 64 is pretty common. So if we take 64 images of our 60,000 and we send it through one forward pass and one backward pass of our model, that would be called one iteration. And then we would take the next 64 images and send that through a forward pass and a backward pass. That would be the second iteration. So we're going to continue cycling through all of our batches, sending it through the forward and backward pass. And it's eventually we're going to run out of images. We get to 60,000. That would be one epoch. And we're going to continue sending more images through the data again, just keep repeating and repeating, and then until we get 2 epochs. Usually for a smaller data set like this, we're going to repeat until about 5 to 10 epochs. And if you have a bigger model, or if you have more images to send through, maybe you want to do a couple more epochs. Now, more epochs doesn't mean it's good. It just means that you also don't want to overfit your model. We talked about that in last episode. Now, to pivot back to loss functions, there's several different loss functions that we can use to help determine how far off our predicted value is from the ground truth labels. Now, the different loss functions depend on what you're trying to solve, what kind of data you're dealing with. If you're doing a regression or if you're doing classification like we are, it all just depends what you're looking into. We're going to be going over just 2 main ones, the mean square error and the cross entropy loss. So to start, the mean squared error is a very common one that's used in a lot of regression tasks. So that's for like home prediction prices. And the Y value right here is the true label, and then the Y hat is our predicted value that we get from the model.
Need to unload our shares before then. Vincent, I'm on it. Bree, be discreet. Vincent, of course. Bree, oh my God, did you see Brian's hat? Vincent, oh fuck, ha 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 ha.
What the hell?
So the loss here would be calculated by finding the distance between the true label and the predicted label that we have. You square that value, and then you average out that value with all the whole entire set. So this method is very popular for things that have continuous numeric values that are keeping added to it. So like predicting a house based on the number of rooms that it has, number of previous owners, maybe the location. Another example might be for a stock prediction. You might have different values that you're trying to input, and then you try to find the correct distance away that you are from the true predicted value. Some more examples might be something like super resolution, where you take an image and then you compare that to a ground truth high resolution image and try to enhance the original image with it. You might have something like depth estimation, where you compare and predict the depth maps to the actual ground truth depth measurements. And then you might even have something like denoising, where you're trying to evaluate how well your image can be enhanced by removing the amount of noise that's filling up your image. So the other loss function we're going to be using is the categorical cross entropy, or just cross entropy. This one's really good in computer vision because it deals a lot with predicted probabilities on how well the image was predicted compared to the ground truth label. So after our softmax function produces values that are between 0 to 1 for each class, we're going to be taking those output values, y hat, and inputting them into our cross entropy equation.
Loose ends. Vincent, we're all good. About to be way better. Bree, smiley face emoji. Vincent, did you see Brian's hat? He's still fucking wearing it.
What the hell?
Bree.
So the beauty in this equation lies in the y value right here. Now this will set our true label to 1 and then set all the other values to 0. So this will really isolate just the true value that we want, and we don't really care about any other of the false values. This was also known as one-hot encoded values. The cross entropy function applies the negative log to our model's predicted value, meaning that if the model was inputted with a probability that was close to 1 for the correct class, that log value would be small, giving it the low loss, which is really good. But if our probability was closer to 0, maybe it's like 0.35 or something, the log shoots up. And that means that the log value would grow much, much larger, and our model would need to be adjusted a lot more. And in general, a high loss value is not very good, and then a low loss value is pretty good. So remember our analogy of trying to aim at a dartboard and get closer and closer? We want to have the lower loss value so we're closer to the target. And in the next video, we're going to be talking about how the model actually adjusts itself so that it can get closer to that dartboard bullseye. And we're going to be talking about optimizers, which uses this loss function value output so that they can adjust the weights going backwards through the system.